looking at subsets with tidyverse is a great tool to have, because you can use that to already start to get an idea of what your data looks like. So you can start to look at which columns you have, or what data points fit certain conditions with filter. So we're going to talk about both select and filter, and select is used for columns and filter is used for rows. So let's start with select. So you may be familiar with the traditional R syntax for calling a column, which is the data frame name, a $, and then the column name. That's the way that base R deals with columns. But the tidyverse has this command called select. And select basically just pulls out one column or multiple columns and returns it to you. It may not look any more convenient than the traditional syntax on first glance, but you can more easily integrate it into like a tidyverse stream of commands or into like a long piped process. So all you have to do is call the column name. You don't need any quotes, just the plain column name, and it will pull out that column. So here you can see our response time column from the self-paced reading data frame, and it just pulls out all of the data points from that column. But say we want to see a little bit more than just like a long list of response times. So we want a little bit of context. We can also pull out more than one column. So say we want the participant ID, what word they were reading, and then the response time. Then we can select participant, word, RT, just list them, no extra punctuation necessary, just the names of the columns. And then you'll pull out all three of those columns. So you have participant, word, response time for the entire data frame. You can see here I called participant, word, RT. If I called RT, word, participant, it's going to pull up those columns in that order. So the order that you give the column names matters to how it's displayed afterwards. And if you're thinking, okay, what if I don't want to write out every single column name in this select call, you can use this everything command and call select and then whatever column you want first and then everything, and then it will follow with everything. So if we call RT and then everything, we'll get the response time column, and then we'll get all other columns in their original order. This is similar to another command in the tidyverse, which we're not going to cover today, which is called to relocate. So relocate will also like help you put columns at the beginning, or if you wanted to put RT following condition, you could put it exactly where you wanted it. So if that's something that you're interested in, then make sure to take a look at relocate. But otherwise, this everything command is pretty convenient for calling columns in order, reordering columns. Okay, so that's the kind of base usage of select, but you can also use select to remove columns. And for that, you just have to use the minus sign. So in this self-paced reading data here, we have this X1, this item type column, and you can see it's a factor with one level, and all it says over and over and over again is just dashed sentence. So that was kind of a leftover of our experimental software. So say we don't want that in the analysis because it's a useless column, then we can select minus item type, and that will automatically select all columns except item type. So it will basically just drop item type. So you can see it's gone there. So select with minus is used for dropping. You can also remove multiple columns at once. For this, you're going to have to wrap your column names in this array syntax, which is the C, or combine. So that basically tells R that this minus should apply to everything inside of the array. So if we select minus and then we wrap it in this C syntax, item type and X1. So X1 is kind of our other useless column. It just has row numbers in it. Then we can drop both those columns at once. And here, so we can take a look at what it looks like. It has those columns dropped. But I'm going to go ahead and assign this back to SPR. I want to replace the SPR that I have in my environment right now with this new one that doesn't include these columns. So I'm going to assign it over top, basically overwrite the one that I have. So when I do that, you can see in my environment that now my SPR data set has 2 columns less. Okay, so those are the base uses of select. So either to like reorder columns or to pull out a subset of columns or to drop columns. But there's also kind of a couple of helpful things you might want to know, especially if you have a data set that has a lot of columns and you don't want to write out like a long list of columns. So there's a couple of helper functions. One of those is ends with. That's going to find any column name that ends with a certain string, a certain piece of text. So for example, in this data set, we have sentence number and word number, and they both end with _num. So we could select all the columns that end with _num. And here we're using quotes, right? So we're using quotes because this is like a text string that we want to match. Basically, the rule of thumb for a lot of these tidyverse commands is if it's not in quotes, it's probably a column name. So something that exists already as a variable in your environment. But if it has quotes, it's more likely to be like a random, not random, but just a string of text that you want to match to. So here we want to match to this exact text. So we're going to select all the columns that end with _num. And you'll see that does exactly what we wanted it to do, and it pulls out both sentence num and word num. I don't think I have to explain what starts with is. It's just the opposite of ends with, except for something that starts with that string. And a really similar one is contains. That will just match this character or string or text, partial name, anywhere in any of the columns. So here pulling out the underscore columns will pull out the same, or you could easily like pull out any column that has an O in it, or you could use multiple string, like any column that contains word. And that just helps you pick out columns a little bit more easily. And finally, what you can do with select is you can select a range. So if I want to pick all the columns from condition to RT, then I can select the columns from condition to RT. So the colon basically means that it's every column from the first one to the last named one in the order that they're given. And you can also do this numerically, like the first to third column could be pulled out with 1 to 3. And you just want to be careful if you're relying on this later on in your piped sequence, because if you somehow change the order of the columns and don't realize it, or for whatever reason the order is changed, then of course these indexes like this are going to change. So just be careful when you do that you know that the columns are definitely going to stay in that order. But if you do, then that can be kind of convenient. A couple more you might want to look into if this is something that you need. There's matches, which can be used with regular expressions. So if you have really a lot of columns and you need like a regex to pull out certain columns, that can be useful. Or num range will help you if you have columns that are a combination of like certain text and then a sequence of numbers after, like x1, x2, x3, x4, which can sometimes happen if you read in columns that don't have names. Okay, I'm going to go on to filter, which is the other subsetting command of tidyverse, and then I'll take questions after that. Okay, so filter is kind of the other subset command in the tidyverse. So select we were using to look at columns and pull out different columns or look at like a slice, a vertical slice. But filter lets you look for rows that fulfill certain conditions. And this makes it one of the easiest to use and most useful parts of the tidyverse in some ways, because it allows you to get like a first look at your data and what groups it's in, or where the values lie. You can look at all sorts of different conditions and combine them. So you can see our little monster friends here. The basic syntax for filter is that you give it the data frame, and then some logical conditions like the type is equal to otter or the site is equal to bay. We can combine different conditions and it will just pull out the rows that fit those conditions. So when we're working with filter, we have a couple of options on how to make logical conditions. You can use this equals to check if something is identical to something else. And just note here that it's 2 equal signs. The reason for that is that 1 equal sign often means like assign this value to this variable or something like that. But the double equals is basically asking R to check if the two things are equal and to return like a true or false. So don't try to set this thing equal to this, but just check if it is equal to the other thing and return true or false. The opposite of that is not equal to. This exclamation mark is often used for not in R. So not equal to, just if two things are not the same. We have greater than or greater than equal to, less than and less than or equal to. Those are self-explanatory. Just keep in mind that you don't do something like one condition is greater than 5 and the other condition is less than 5, because then you'll be left with an actual 5 not fitting either of those conditions, right? So keep in mind that there's the greater than or equal to. And finally, there's in that allows you to match to multiple options. But I'll show you an example of that. That'll become clear. And the basic syntax is that you can pipe the data into the filter command. You don't have to. You could use it as the first argument, but it's going to be a lot more useful if you can pipe it in, because then you can kind of keep going with some other tidyverse steps later. So say you decide to pipe it in, then you do the data and you filter, you give filter and then the column name you want to filter, and a condition based on a logical operator. So logical operator here and then the condition. So with the self-paced reading data, say we want to filter the response times and see if any are under 200 milliseconds. Then we can do SPR, pipe it to filter. The column we're dealing with is RT, and the condition is less than 200. So that would just pull out all the rows where the response time is less than 200. And an easy way to see kind of how many of these, how many we're dealing with here, is you can look down here. So this has 693 rows. So that means that there were 693 response times that were less than 200 milliseconds. Similarly, we could look at like the response time is greater than or equal to 250. That would just do the opposite and pull out slightly longer response times. Okay, so this I've commented out because it's going to throw an error, but so let's say we want to look at like everything that's in condition A cat. So all of our, I think those were like our matching, yeah, our matching colloquiums for cats. Then you think, okay, let's try and like check if the condition column is equal to condition A cat. That will throw an error because it says it can't find condition A cat. And this goes back to my rule of thumb here with the quotes or not quotes. So if it doesn't have quotes, like this didn't have quotes, then it's going to look for that thing in the environment generally, look for either like a variable or a column name that matches this, which of course it doesn't find because we're just looking to match like this text. So you can probably imagine that the fix to this problem is to put any sort of character or text string that you're trying to match into quotes. So if we filter that condition is equal, double equal to quotes, condition A cat, then that will work and do what we expected and pull out all of the condition A cat sentences. Now, something that you have to do a lot with linguistic data, especially with like experimental linguistic data, is drop practice sentences. So say we had this in our self-paced reading here, we have like some practice sentences where the participants were getting used to the experimental design. And we've denoted those with the entry practice in the condition column. And we want to drop those. Okay, so what we want to do there is we want to filter that the condition is not equal to practice. So that we have any other condition, but just not practice, right? And we want to save that, of course, because we want to make sure that we keep that going forward. We don't ever want those rows to be back in again. And you can easily use filter to drop these just like this. And here, what I would recommend, or what I always do, is I will check the number of rows that the data frame has before and after. So often you're going to need to report like how much data you've lost, or you also just want to make sure that you're not doing something crazy. Like maybe you think you have 5 practice questions and maybe there was some data entry problem and you end up dropping half your data set. So I always do this n row, and then you just call just a data frame name before and after. So we'll do that, and then we'll remove the practice, and then we'll call it again. Oops, if I would have done that in one row in one step, then it would have printed out the before and after. So let's try that again. Yeah, so if you run it in the code block like this, and you just press on the arrow, then it will print out like the before number of rows and the after number of rows, and you can see how much data you've lost there. So here we've lost about 250 rows. But anyways, that way you can use filter to remove items that you don't want, like practice items. There's also in, and in will allow you to match multiple options. So if we want the words cat, so anytime there's a response time to reading the word cat or dog, then we can filter that the word is present in the array cat dog. So again, here we use the sort of C syntax. This is the vector syntax in R to tell R that we're giving it multiple options, like multiple things that fulfill the same role. So here the role would be like thing to match. And so we can filter that the word is in this array. So basically that it's either cat or dog. That will pop out all of the cat and dog rows. And we can also do this like with numbers. I just wanted to show that so you can see that those that numbers don't have quotes, just that numbers are just plain. So if we want sentences 4 or 14, then we can pull out sentences 4 and 14. The capitalization does matter here. So like if I try and write cat with a capital C here, then you'll see it only pulls out dog because it doesn't find cat with a capital C. So it's totally case sensitive, and it matches exactly to the string that you've given it. Okay, so what if we want to do more than one condition? Then we can easily combine conditions using either the and sign, which would be and, which means that both conditions have to be true, which is what you would expect. So it's same as in language. Or you can use this straight line for or. And of course, that means that just one has to be true. And if one is false, then that's okay. So say we want to look at reading times where the word was cat and the reading time was over 300. Then we just write these the same as we would in a normal filter call and combine them with and. So word equals cat equals cat, and the response time is greater than 300. And that will do what you expect there. Or here we wanted to look at maybe like the extreme response times, then we could filter for RT being greater than 600 or the RT being less than 100. And that will pull up like all of the small, but also large RTs. So basically you just have to combine your conditions with either the and sign or this or sign. So you can also, so what makes a tidyverse so useful is that when you filter or do anything, sort of mostly anything in the tidyverse, you can chain different functions. So you can use the pipe to complete steps in order, but kind of at the same time. So like it still proceeds sequentially from the first thing to the next thing, but you can run them as one chunk of code. So say we take the self-paced reading data frame and we send it to filter, and we pull out only the ones where the condition is condition B dog. Then we can take that, so now we only have the condition B dog sentences left, and we can select like just 2 columns. So we could select word and response time, and this is going to pull out only the word and response times columns for the rows where the condition is condition B dog. So this always happens in order. So if you want to check what is going on, or like if I'm working on some complicated data wrangling task, maybe I'll first check what this part does, so the condition B dog part, and just check that that looks like it's kind of what I was hoping for. And then you can add on the next steps, like selecting the word and response time, and yeah, get a look at only those 2 columns. Something else I want to show you here with filter is an easy way to pull back all of the unique items. You'll see why this is useful. So say you want to look at all, so like you're unfamiliar with this experiment, so you want to know which sentences showed up in the condition B that had to do with dogs. So what you can do is, again, the first step is to filter so that the only data that you're looking at or have left is that for which the condition is condition B dog. That's what's happening here. So we're just pulling out all of the rows having to do with condition B dog. And then we can pull up distinct sentence, and that will pull all of the distinct items in the sentence column that are left here. Let's go ahead and look. So it's just going to pull up these 5 rows because those are the only unique items in the sentence column after this filtering has been done. Distinct on its own without any column name here will pull up any row where every item is unique. So where at least one column is different than, like the entry in at least one column is different than at least one other row. But if you give it a column name, it will pull up the unique items in that column only. And you can also use this to do like a unique combinations of values. So say we want to look at, here we're not filtering, we're just looking at the whole data set, and we want to look at all of the unique combinations of sentence and condition. Then we'll see, it doesn't quite fit on my screen here, but you have all of your conditions and the sentences that show up on in that condition. So if I had a little bit bigger screen, they would show up next to each other, but you can see that like in condition A, cat, that the sentences were these first 5 or so, and so on. So that's a way just to look at the unique combinations in your data. And something else that might be useful is dropping NAs. So you might end up with NAs in your data set at some point. This is pretty likely to happen at some point in your data analysis. It could be that this cell was empty, or that somehow it didn't fit with the right data type, or there's a lot of reasons why you might end up with NAs. And basically that just means that that cell is empty or not really usable by R, and it will end up just showing an NA. So you can use here, this is NA. It's a kind of a helper function, which actually comes from base R. And that just returns true if it's an NA and false if it's not an NA. So it's really intuitive. The only thing is what you want to do is say not, right? So remember the exclamation mark means not. So here, if we filter this part of the command, means is not NA, or not is NA. So reverse what's happening here. So here we can filter for response time is not NA, and the word is cat. I don't think we actually have NAs in our response time column in this example. But if we did, then it would drop them here by this part with the not NA, not is NA. And tidyverse actually has its own command for that too, which is called drop NA. You can, if you use drop NA with no argument, so just like this, it's going to drop every row in the entire data set for which there is an NA anywhere in any of the columns. That's pretty dangerous. So say you had like in the gender column for one of your participants, it just says NA because they didn't answer. Then if you dropped NAs from your whole data set, then that whole participant would be completely lost. So you have to, yeah, be careful with dropping NAs. If you do decide that that's what you want to do or that it makes sense for you, then just be careful to check like the number of rows before and after. You probably want to do it based on columns. So give the column names that you want to drop from. And not just drop blindly. Yeah, so I just want to mention that drop NA is an option. You also can drop it as part of a pipe sequence. So if you don't want to like save this back, you don't want to permanently delete all the rows that have NAs in the RT column, you could just like drop the NAs and then continue on to do whatever you need to do next, filter or whatever type of command you want to do. And if NAs are a thing that you deal with a lot, then there's also the replace NA command that will allow you to take an NA and replace it with a number that makes sense. So say your NAs are supposed to be zeros, then you can replace them with zeros. Yeah, so that's how you work with subsets in R. Again, with columns is select and with rows is filter.